So in class we were talking about what this term was. That was f of k naught, where these are vectors, that was buried inside and was really the form factor. Now, the only way we can really solve for this, let me just write what the equation was that we had. We had that the such that psi of the scattered wave was going to equal f, I can switch these if I want, k naught k times e to the I k times r minus r prime over r minus r prime. And we wanted to find what this guy is. So how do we go about and do that? Well, the problem is we can't get this unless we know what this is. And how do we know what that is? Well, we know what that is because that's a wave function for an electron. And so it is subject to the Schrodinger equation. So we're going to need to solve the Schrodinger equation to get psi, which will then give us f of k naught k. So that's the plan. Okay. The Schrodinger equation, what is that? Well, you must remember it. Minus h bar squared on 2m times the Laplacian del squared psi of r prime plus v of r prime times psi of r prime, and that's going to equal e psi of r prime. Okay. How do we solve this? Well, the first thing we do is transpose. So first, transpose. So that's going to give us h bar squared on 2m del squared psi of r prime plus e psi of r prime. It's going to equal the other stuff, v of r prime psi of r prime. Next, we're going to make a substitution. So now we're going to let k naught squared equal 2me over h bar squared and u of r prime equal 2m over h bar squared times v of r prime. Now, why are we doing this? We're doing this because we want to simplify this equation. I think you can see that if we plug those values in, we will indeed get, we can pull out an operator, so we get, we will get del squared plus k naught squared times, or operating on psi prime, and that'll equal u of r prime times psi of r prime. So that's pretty slick. We have a nice operator equation. But why did we make those substitutions? Where did we come up with that? Well, you might remember. So I'm going to just call this an aside. Remember, so de Broglie said that H equals lambda p, and that equals lambda times m phi. We assume that a free electron only has kinetic energy. So what does that mean? Implies that E kinetic equals 1/2 mv squared, or V equals 2e over m, the square root. So now that we have V, we can find a relationship with lambda and V, because we get that from up here, H equals lambda m, and we're going to put in V, times the square root of 2e over m. Bring the m inside the square root, lambda times the square root of 2m squared e on m, cross our m's out, and we finally find that lambda will equal, 1 over lambda will equal 1 over h square root of 2m e. Well, that's pretty close to what our value is up here, but not quite. We have that funny, pesky little h bar. So what's going on with that? K naught equals 2 pi on lambda for our application. So we need to put 2 pi on each side. So K naught equals 2 pi on lambda, which equals 2 pi on h square root of 2me, but h bar equals h on 2 pi. So that means that K naught equals 1 over h bar square root of 2me, and squaring both sides, K naught squared equals 2me over h bar squared, which is the same result. Okay, back to our lecture. I'm going to write this down again, what we had before. Actually, I can just copy what we have. So we're going to take this and we're going to put it right here. Okie doke. So now we're all set. We've got a nice operator equation, and all we have to do is solve this. This is a partial differential equation. A partial differential equation, which means hard to solve. Why? Because you have an uncountable infinity of solutions, and the only way to do these is to find characteristic lines, to find the Monge cones, because you can have many different possible solutions to this, which make it really, really hard. There is an alternative approach, though. And the alternative approach is that you can use something called a Green's function. Now, what's a Green's function? Hard to solve, but one way is to use a Green's function. What's a Green's function? Well, a Green's function is a way to turn a partial differential equation into an integral equation, which can then be done numerically. This was first thought up in the 1880s with a guy named George Green, who never even went to school. He was a self-taught mathematician, and he thought of this idea. And the idea was, if you could find an auxiliary function which, when operated on, turned into a delta function, then you could apply to both sides and integrate. What's that look like? So in our case, we need to find a function g of r and r prime such that del squared plus k naught squared operated on by g of r and r prime equals delta of r prime. So it brings any r and r prime into a delta function of r prime. Okay. The book shows you how to find one. In general, this is very difficult. But if you do have one, and for this particular case, you can get one. So I'm just going to put shows how to get one for del squared plus k naught squared. And the result is that g of r prime equals minus 1 over 4 pi e to the I k r minus r prime. Whoops. R minus r prime, these are absolute value signs, over r minus r prime. And so, since this works, you can verify it yourself. So now use it. So we're going to take this on both sides, and we're going to end up with psi scattered from above of r is going to equal the integral of u of r prime, psi of r prime, g of r prime, and integrate it over some volume with r prime over the volume of the atom. And there you have it. This is an integral equation which represents the equation, this original equation, which I'll just remind you was up here. So by putting, in here, g of r prime, and you multiply this times g of r prime, and then you integrate both sides, and you're going to get popping out exactly what we wanted to do. Okay. So that's how a Green's function works. I'll just take those out of there. And we'll go back to where we were. So we end up with this equation. And we can now use this. So use it. First, put incident and scattered waves together. So psi incident plus psi scattered equals psi, which is going to equal e to the I k naught dot r, that's the psi incident, plus 2m over h bar squared, integral of v of r prime, psi of r prime, g of r prime, d r prime cubed. So this is an exact representation of our system. But there's a problem. The problem is we have psi here and we have psi here. So what do we do? Well, what we need to do now is what's called the firstborn approximation. But I'm going to stop right here, and we'll do that in the next short video. So I hope this makes the book a little bit easier to understand. I hope so. Okay, we'll do another one later.